Next, we will discuss the measures of variation or spread that describe how much data varies from the center. Consider the two sets of players. The mean of each group is 75, but clearly the two teams are not the same. One of the differences between the two teams that any measure of the center doesn't capture is the variety of data within the set. To describe that difference quantitatively, we use a descriptive measure that indicates the amount of variation or spread in the data set. Such descriptive measures are referred to as measures of variation or measures of spread. Just as there are several different measures of center, there are also several different measures of variation. In this section, we will examine the most frequently used measures of variation. One example of a measure of variation is the range. The range of a dataset is the difference between the maximum and minimum observations. For example, the range of team 1 is 78 minus 72, which is 6, and the range of team 2 is 84 minus 67, which is 17. The range only measures the total variation and doesn't capture any variation between the minimum and maximum observed values. It's not the only nor the best way to measure the variation. In contrast to the range, the standard deviation takes into account all the observations and is the preferred measure of variation when the mean is used as the measure of center. The formulas for finding the standard deviations of a sample and the population differ slightly. First, let's assume that we are dealing with the population. First, we are going to list all the values in the first column and compute the population mean mu, which is 75. Then we will subtract the mean from each observation to make sure that all observations are accounted for. So if we were to add these differences now, then we would have gotten a 0 total, which is not what we want. So next, we square each difference to count each variation as positive. And only now it makes sense to add them all together to obtain 24, the sum of squared differences. However, the total sum of squared differences is not a good way to measure the variation, just like the grand total of a student's grades is not a good way to measure their academic achievement. So we naturally divide by n to find the average, which is 4.8. This measure is labeled with Greek letters sigma square and is called the population variance, and is very significant in theory. However, from the practical point of view, we can make it better. Next, we take the square root and obtain 2.19. This measure is labeled with Greek letter sigma and is called the population standard deviation. And its advantage is that it has the same units as the original data, in this case inches, and therefore can be used as a measuring stick. Roughly speaking, the standard deviation measures variation by indicating how far on average the observations are from the mean. For a dataset with a large amount of variation, the observations will on average be far from the mean, so the standard deviation will be large. For a dataset with small amount of variation, the observations will on average be close to the mean, so the standard deviation will be small. In the data where all values are the same, the standard deviation is equal to 0 as there is no variation. Remember, do not perform any rounding until the computation is complete. Otherwise, substantial round-off error can occur. Now let's assume that we actually are interested in the standard deviation of the heights of all players in the league, but we have only accessed the given 5 players, which are now became a sample. So now we will label the mean as x bar rather than mu, and will perform the first few steps in the same way as before until it is time to divide. Next, we are going to divide by 4 instead of 5. I will explain why later, but for right now, let's just register the fact that to compute the sample variance, we divide by the sample size minus 1 rather than the entire sample size. And we'll label it as s squared. We finish by taking the square root and obtaining 2.45. This measure is called the sample standard deviation, and it has the same units as the original data, in this case, inches. We'll label it with a letter S. We only use this approach when dealing with samples. Usually we use the same formulas for computing the population's parameter and a sample statistic. However, as it became obvious, it was not the case with the standard deviation and variance. So why do we divide by n-1 instead of n? Remember that the main purpose of finding a statistic is to estimate the unknown parameter, in this case sigma squared. To do that, we use the sample variance as squared. If we divide by n instead of n-1, we will be obtaining a value that is always underestimating the true population variance by a factor of n over n-1. After the correction, we get a formula for the desired unbiased estimator for the population variance, which we call a sample variance. We discussed the most frequently used measures of variation or spread that describe how much data varies from the center.